Lab 2, line of charges. The purpose of Lab 2 is to use a computational model that visualizes and calculates the interactions between two charged pieces of tape in order to estimate the excess electric charge on the piece of tape by treating the tape as a line of charge that's evenly distributed across the surface of the tape. We find that the gravitational force magnitude on the tape is 1.96 times 10 to the negative third power newtons. Using our model for Lab 2, we find a new charge that gives us an electrical force that is equal and opposite to the gravitational force, and the new charge is 2.26 times 10 to the negative 8th power coulombs, which is larger than the charge estimated in Lab 1. Here are some fundamental principles explored in this lab. Are first the application of the electric field of a point charge in order to find the electric field and force of an object with uniform charge distribution. Next, we find that our experiment involves Newton's second and third laws of motion, where the second law is observed through the two charged tapes having gravitational force and electric force that are equal and opposite to each other to create a state of equilibrium, and the third law where we observe in the interaction between the bottom and top tape as they approach each other. Finally, the concept of charge distribution in this lab is important, as we are now treating the charge tape as having distributed charge that can be segmented into very small pieces, whose electric fields can be summed to find a net electric field using the principle of superposition. Here are observations and data collected from Lab 1. We found that a piece of U-tape was positively charged because it was attracted to a negatively charged plastic pen. The length and mass of the U-tape was also measured, as well as the separation distance between two pieces of U-tape when tape B began to float above tape A due to the like charges repelling. The distance was 0.02 meters. The actual experiment involved making two U-tapes and placing tape B between two books and approaching from the underside with tape A. The assumptions that were made in Lab 1, that air resistance is negligible and each U-tape has the same net charge with no charge transfer, still applied, but a new assumption made for Lab 2 was that each U-tape can now be treated as a line of charge that has charge that's evenly distributed along the surface. In Lab 1, we treated each U-tape as a single point charge, whereas now we are treating each U-tape as a line of point charges. The white and yellow arrows represent the electrical force exerted on tape B by tape A and the gravitational force on tape B, respectively. The smaller green arrows in the Lab 2 model represent the individual electrical fields exerted on each point charge on tape B. Here is how we calculated gravitational force initially, where force is equal to mass times gravity. And electric force should be equal and opposite to gravitational force because at the moment before tape B begins to float, due to the electric force from tape A overcoming gravitational force of tape B, we can say the system is in equilibrium and therefore the net force is zero. Using a computational coding model, we had to use trial and error to find the new accurate charge that gave it electrical force that was equal and opposite to the gravitational force. The charge was 2.26 times 10 to the negative 8th power coulombs, using a model with 10 point charges making up the line. Here is the bulk of the computational code used to find the new and more accurate charge of the tape. We had to assume that the line of charge on each of the two tapes could be segmented into smaller pieces of charge that are treated as point charges. The first function shown calculates the electric field due to a point charge from tape A at an observation location on a point charge on tape B. At the location of each point charge in tape B, there is an electric field produced by the collection of point charges that make up tape A, which is represented by the first formula shown in the lower left-hand corner. Using nested for loops as shown in the picture, we can calculate the total electric force on tape B due to tape A by adding up the electric fields from each point particle in tape A as they interact with each point particle in tape B and multiplying by the charge of tape B. This is also represented by the last two formulas shown in the lower left-hand corner. Here is the computational model outputs using the new computational model code. Inputting the charge estimate in Lab 1 into the code, we find that the electric force due to this charge is not equal and opposite to the gravitational force. On the other hand, using our model in Lab 2 and a new charge that gives us an electrical force that is equal and opposite to the gravitational force, we find that the charge is 2.26 times 10 to the negative 8 power coulombs. Here are some questions to think about. What if you had modeled each of your tapes as a single point charge, like in the previous lab? The charge of the tape when modeled as a point charge was 9.33 times 10 to the negative 9th power coulombs, whereas the charge of the tape when modeled as a line of charge was 2.26 times 10 to the negative 8th power coulombs, which is a larger value than the Lab 1 estimation. The Lab 1 charge was an underestimation. Why do these estimates differ, and which value is more likely to be closer to the real value? Well, the charge found by the point charge model is a generalized estimation, whereas the charge from the line charge model is a more accurate to real-life application where the distributed charge is accounted for, giving more charge over distance to consider versus that of a single point particle of charge. In conclusion, In this lab, we learned that the line charge model is a more accurate representation of a piece of tape than using a point charge model like in Lab 1, because we are able to evenly distribute charge over the length of the tape by applying the superposition principle to find the net force. We found the electric force exerted on the tape is 1.96 times 10 to the negative third power newtons and is equal and opposite to the gravitational force on the tape. And the charge on the tape was more accurately estimated to be 2.26 times 10 to the negative 8th power coulombs.